all about the Lenz's law. Now let's move down to Fleming's right-hand rule. Fleming's right-hand rule, this is the right hand. We talked about left hand. The idea is just the same. The only difference, you ready for that difference?
Yes.
Guys, you ready for the difference, huh? All right.
Yes, mister.
This is the difference. The difference is that you look at the thumb. Initially, we know that from the left hand, the second finger here, it gives you current, which is still the same. Finger points towards the field line, this is still the same. But the thumb here, it actually gives you the force. From the left hand rule, it used to be force. But right hand, it's not force, it's the motion. That's the difference. You got the difference already?
Yes.
Yes? All right. Now, Fleming's
yes.
right-hand rule is closely used with the concept of moving. I have underlined this and made it to be like, colored that red. I used this red ink because it's important. Fleming's right-hand rule is associated with anything to do with movement, motion, anything to do with that, always remember the right-hand rule. Anything to do with force, you have to remember the left-hand rule. Clear?
Yes.
Right.
Which one is the right hand?
I repeat. Fleming's left-hand rule is used whenever you see a setting like that, whenever you see a setting like this. But here, instead of direction of motion, if they give you something like force, if force is involved in a setting like that, then obviously you're using Fleming's left-hand rule.
That means left.
But if force is missing and the word like motion or movement, any one of them is given, then it is the right-hand rule. Understand?
Yeah.
Understood.
Perfect. Let's move a little bit further down and check out this example here. Now let's check this example. What is the direction of movement of the conductor? This is the conductor here.
Yeah, I'm not crying. I don't understand.
Can you see this conductor?
I don't want one more banana.
All right, class, I have actually indicated the conductor, and that conductor is placed within the magnetic field. What is the direction of movement of the conductor, which is free to move on two wires in the magnetic field produced by the magnet? In which direction do you expect this conductor to move? A, B, C, D, or E?
That's true.
Class, you're using Fleming's left hand or right hand rule?
Right hand.
Right hand, okay. Why do you have to use right hand? Because of the word
It's asking us for the movement.
Because of the word movement. Can you see it?
Yeah, Mister, it's asking for movement.
That's right.
Yeah, it's right. Rule.
Okay, because of the word movement, I am using right hand rule. Now let's use right hand rule. Use your right hand rule and tell me, try to figure out. I am going to give you the final answer. Field lines, they always go from north to south, so use your finger. Go from north to south, like that. It's going down.
This thing, like the one it's for the right hand only, the right hand, left hand. There is two.
Right hand. You're using right hand rule. Field lines going from north to south. Current is going this way, plus, notice I am going to give you the current direction. Current is going this way, and it's going across that way.
Amen.
Can you see that?
I'm gonna put it like this. This is the motion. This is the current direction.
The line is going down. Current is going out that way. So which one? Tell me which direction? A, B, C, D, or E?
E.
A. Yeah. No. That was
E.
A.
E,
B.
mister.
B.
Now the answer is B.
Oh.
Oh.
Oh, now me.
Use your right hand. Use your right hand. Use your right hand and figure it out. Figure it out.
right. This is the
E.
field line direction.
What the heck?
Pointer is the field line direction.
It's going from north to south. Current direction.
Field line is from north to south.
Mr. What?
Have you figured it out yet?
Yeah. It's D.
Oh yeah, mister. Yeah.
All right, good. Is everybody okay with that? Tell me.
Mister, can you explain?
No.
Okay.
Mr. Show your fingers.
Here. Okay.
Mister,
Tom is going
can
down
you
this
explain
way.
again, please?
Yes.
Mr.
Can you
Start again, Mister.
Oh my God.
That's why you don't speak with your fingers.
Okay.
Yeah, mister. I wanna see your finger.
Explain.
Just remember that funny. This is going to be really funny. I imagine this left hand and I had to change the position of my.
Yeah.
What were you
Tell me.
What were you
Okay.
thinking, though?
Now field line.
Hey, shut up. You don't
Guys, here notice. Field line going from north to south.
Yeah. Can you look at this?
Current going from.
You know
Can you
what?
see this?
About to have fun when I go under.
Yeah.
Power of the
Yes.
snell beginning.
Yes.
Okay. So which means that it can never be B. It can never be E.
Oh.
E.
It can never be C because C is actually what is it? Current direction. Can you see that?
Yeah.
The answer falls between A and D. Are you following?
Yes.
Yes. I'm gonna put all the Green Day songs.
So now use your right hand.
But
Feel
like not all, like
feel like
every
going down
song.
this way. Current coming.
But like all the albums.
Yes.
Current going this way, and thumb is coming this way towards D. Can you see that?
Yes.
Oh,
Yes,
what
mister.
are you
Yes.
talking about?
Mister, which way is the current flowing?
Can you draw your
on
fingers
the diagram?
Current
Can
is
you
going
show?
this way.
So many people talking.
Oh, mister,
okay.
I get it. Yeah.
Okay,
So,
thank
mister,
you.
Three lines going down this way. Current is going out that way, and thumb is coming this way. Coming towards D. Can you see that?
Yes, mister.
It's coming towards D.
But mister, that's your left hand.
Oh, so then it's
Motion. You're looking for this.
Leandra?
just D.
D.
Yes.
Is that clear with
Mr.
everyone?
Fleming. Mister, can you draw your end on the border?
That's clear with everyone?
I can't do this.
Okay, listen up. Guys, listen. If you do not understand that, the email address is down there. So I'm going to ask you to, if you got a question, you can forward it and I will answer on that.
Thank you, Mister.
Okay, let's move a little bit further down.
Okay.
Let's move a little bit further down. Check
Yes,
this
sir.
out. Check this example now. Now you check this example. The diagram shows a straight horizontal wire moving. Again, I have underlined. Remember those examples, I am making it obvious for you. I have underlined the word moving just to make sure that you are, when you see this word here, moving, it tells you that it is the right-hand rule that you're using. So it's moving vertically down the magnetic field as it's given down here. Identify the current direction. Can you do that? Field lines, they run from north to south. Field lines running from north to south. Use your right hand rule and tell me, let's say if this is A and that is B, will current flow from A to B or B to A?
A to B.
A to B.
A to B.
A to B.
The line right this way.
A to B.
It's B to A. Yeah.
Oh no, it's B to A. Yeah, B to A.
A to B. Oh.
B to A.
B to A.
B to A.
B to your A.
Yes,
Yeah.
going from B to A.
Yeah,
B to A.
yes.
Dom, did you get that? Dom,
Wait, don't.
Yes.
Wait, don't
I think it.
Yes, mister.
did you get that?
My name was so few.
What is
Mister,
that?
he can't, I mean, he can hear you, but he can't respond
all
because
right.
it's
So left.
Yes,
So
sir.
that's
mister.
that's okay with everyone?
Yes.
It's okay with everyone, huh?
Yes.
All right, let's take a
Yes,
look at the
mister.
next one here. The next example. 3. A horizontal wire carries a current between two magnetic poles, N and S, north and south, as it is given below here. The direction of the force on the wire is direction. This time it is talking about, what is it?
Force.
Left and right.
Direction of force. I have
Yeah.
underlined this.
Force.
What does that
Left
mean? Are you using right hand or left hand?
Left hand.
The left hand. The left
Use your
hand,
left
mister.
hand. Use your left hand.
Mm.
So using your left hand,
It's vertically upward.
which one is the correct answer? A, vertically
A.
upward. B,
A.
vertically downward. C, in the direction of current. D, from north to south. E, from south to north.
Yeah.
Obviously, it cannot be from
So vertically up. A.
not from north to south, not in the direction of the current.
Hey.
Which one is the correct answer?
A.
A.
Hey.
A.
Are you using left hand or right
Hey.
hand?
Left hand.
Left hand.
Left hand, the correct answer is A.
Now
Yes.
me. Now means
So,
hey.
Hey, it's hey, Courtney.
that's right, A.
Yes, mister.
Okay, now let's move a little bit further down and check this out. Check this question. The diagram, we're doing that together. The diagram below shows a circular loop. Here, this is the circular loop. This is the one. A circular loop and a magnet. We got a magnet, North pole and the South pole as labeled already. Direction of motion. North pole is brought closer to the, North pole is brought towards the loop. That's basically a solenoid. You tell me, what should this side be? Let's say this is A and that's B. What shall, when the North pole is brought closer to B, what will happen to end B? What's going to be? It's
Repulsion.
It will become north.
that's right. It
Yeah.
becomes North pole.
Yes.
It becomes North pole. So use your right hand grip rule to identify the current direction.
Downward.
Okay, so current direction is coming down this way.
Mm-hmm.
Yes?
Yeah.
Yes, mister.
All right, this
Yes,
is
sir.
the current direction. The second part, B. How could the magnitude of the current induced in a loop by the same magnet be increased? How can we increase that?
More coils. Increase the 10.
Coils.
Just by the way it is given, there isn't, like, the loop is going to be just the way as it is. What else can you do to increase that?
Mr. Increase the number of
Increase
coils.
the coil.
Increase the coil, okay.
Increase
Increase
The
the
number
coil.
of
That's,
volts of current.
And
What is
the
it?
coil.
you increase the movement here, magnet.
Oh.
Increase
Okay,
the
okay.
movement.
Mhm.
Clear?
Yes,
Increase
Mr.
the speed. Increase the speed. Increase the speed of the magnet. That's how you're going to increase the induced current.
Mister, you mean like bring it closer to the loop faster or something?
Yes, yes, yes. Increasing the speed of the magnet, because once when the magnet is brought this way in, it is done with some velocity. So that velocity needs to be increased.
Okay, Mister.
All
Thanks.
right. Let's move a little bit further down. And I think these are the factors. These are the factors that determine the induced current. And first of all is the speed of the relative motion is increased, like we saw earlier on in the question. The second one is the strength of the magnetic field. Increasing the strength, it increases the induced current. The next one is length of the conductor. The length of the conductor must be increased to increase the induced current. And finally, if we are looking at a solenoid, this is especially for a solenoid, you have to increase the number of, what is it?
Turns.
Number of turns. Number of turns. And the second one, this is especially to do with a magnetic field, a current carrying conductor cutting the magnetic field lines. And that is the magnitude of the induced current. It becomes maximum when the conductor cuts the magnetic field line at 90 degrees. Those are the important factors that you have to remember. Now, application of electromagnetic induction. I am going to go into detail, the detailed bit of this one's. Maybe when you come back in class, I'm going to explain the detailed bit of that. But the application of electromagnetic induction, remember, electromagnetism is using a current to produce a magnet. But electromagnetic induction is using the magnet to produce electricity. Remember?
Yes.
Now, when sometimes we experience blackout and we use the standby generator, the genset. What happens is that the generator is not actually being connected to some source, but due to that the burning of fuel causing the mechanic to work inside, producing the movement, and it produces the electricity. You get what I'm saying?
Oh.
Generator is a common application of electromagnetic induction, because only the movement produces movement, and magnet, combination of all of those ones, it produces electricity. Did you get that?
Yes, sir.
Right. So that's basically that's one of the main application of electromagnetic induction. So like the process, all of this, I am going to explain in detail, maybe in a different session, or if you come back, we're going to talk about this in class. And that is one of those common applications. Now, the difference here, you will notice that this is something similar like what we saw, the simple motor. Do you remember the simple motor? Class, this diagram here. This diagram.
Yes, Mister.
This diagram seems like the simple motor. I am going to, in the final slide, I'm going to show you the difference. And so let's move a little bit further down and check this out. So this is it. Difference between a motor and a generator. Simple motor, simple motor. Look at those two diagrams closely and tell me if there are any differences that you can see. You got a magnet on this side?
And you have a compass on the other something.
All right. So the setting, you'll notice that you got magnet in here, not in the South Pole, not in the South Pole on this side. This okay. You got a coil here. Coil is still the same as you got another coil. Rotation is taking place. You got those commutators and carbon brass and all of those ones, just the same thing. But the only difference is that this bit here, this is an electricity source, whereas this is called a load or some resistor or some lamp, something like that. Can you see the difference?
Yes.
Yes, Mr.
Down here, this is electricity source. On this end, this is a load, something that will use up electricity. This is something that is going to produce electricity. And on that side, it is something that is going to use up electricity. That's the difference. Now that means that on this end you're going to use, when electricity is used, you notice that this end you're going to use Fleming's left-hand rule, whereas this side you're going to use Fleming's, what is it?
Fleming's right hand.
Right-hand rule. Right-hand rule. Clear?
Yes,
Yes,
You're using Fleming's left-hand rule with simple motor, and with generator, you're using Fleming's right-hand rule. That's the difference. Now let's move a little bit further down. Oh, no, don't move further down. We're almost there now. But
Okay.
okay. Class, look at this.
Wink, wink.
Look at this. Importantly,
Stop that.
yes, we're going to stop right here. We're going to stop right here. So the difference is that when do we use Fleming's left-hand rule? Fleming's left-hand rule is when a force is involved.
Force, yes.
When force is involved, you're using Fleming's left-hand rule. When movement is involved,
Yes.
you're using Fleming's
Fleming's
right-hand
rule.
Yes.
Now the difference that simple motor, it is the one that is connected to some source. Generator, the movement taking place here produces electricity, which is used up by the load down here. So that's the whole difference. Otherwise, I think